Ever wonder what 5 seconds would look like on a planet where it literally rains molten iron? We're talking about WASP-76b. This gas giant is about 640 light-years away. It orbits its host star, WASP-76, at an uncomfortably close 0.033 astronomical units. It's barely 4.9 million kilometers. For perspective, Mercury, the closest planet to our Sun, orbits nearly 10 times further out. This ridiculously tight orbit gives WASP-76b a year that lasts just over 1.8 days. We're officially set to broil. But here's the thing. Our Sun, a chill G-type star. WASP-76, an F7-type star, staggeringly hotter and larger, with a surface temperature of 6,250 Kelvin. It emits strongly in the high-energy ultraviolet spectrum, meaning the death you face is not just a bake-off, but a photochemical annihilation in a high-energy plasma. Sounds fun, right? Let's dive in. You cross the atmospheric threshold, and before your brain can even process what's happening, two forces instantly try to flatten and fry you. First, gravity. This massive giant is pulling you in. While it's slightly less massive than Jupiter, its radius is bloated to 1.8 times Jupiter's size, making it a puffy world with a gravitational acceleration of approximately 6.8 meters per second squared. You'd immediately experience a persistent high-speed plummet under a load of roughly 0.7 Gs, less than Earth's gravity but still a fall. Your descent is an instant, violent plummet. You wouldn't even get the chance to regret your decision. Simultaneously, the radiative flux is staggering, causing the ambient temperature on the day side to climb above 2,400 degrees Celsius. This heat is not just a blowtorch. It's a blowtorch on steroids. The host star's UV photons induce molecular dissociation and ionization. This means any material on you instantly flashes into an atomic plasma state due to thermal dissociation. Your phone would fry. Your skin would burn. Verdict: instant surface vaporization, still functioning, for now. Inside the planet's atmosphere, but it's less like air and more like metal-rich fog full of sodium, magnesium, and vaporized iron. Here, the real danger isn't just the heat, it's the sheer staggering kinetic energy, the wind. This planet is tidally locked in orbit, meaning one side is a permanent day, scorching, and the other side is a permanent night, cooler. That huge temperature difference creates unbelievably fast winds. You're hit with hypervelocity air currents. The main wind trying to sweep you from the day side to the night side moves at speeds up to 5 kilometers per second. That's 18,000 kilometers per hour, or roughly Mach 15. This massively supersonic wind is an extreme shear force, instantly ripping apart your structure laterally. It tears you sideways. The combination of this supersonic speed and the relentless thermal dissociation guarantees complete mechanical disintegration. Any remaining material is instantly ablated, or burned off, scattered outward or laterally, and mixed with exotic heavy elements like ionized barium, which is 2.5 times heavier than iron. Verdict: vaporized, scattered, and traveling at Mach 15. Before we get completely flash-fried by that 2,400 degrees Celsius heat, let's hit pause for a second to talk about today's sponsor, Shortform. Look, understanding WASP-76b in space in general requires serious analytical horsepower. And when I'm trying to learn a complex book or topic quickly, I use Shortform. It's not just some quick AI-generated summary. The team at Shortform creates deep, analytical guides that give you chapter-by-chapter breakdowns and smart commentary. They connect ideas across different books and even give you counterpoints. It's the real breakdown you need, not just an abstract. Not only do they analyze books, but also articles, or they even give you a detailed summary of your favorite podcast. Plus, their browser extension is amazing. It can summarize literally anything online, articles, emails, even YouTube videos with a single click. It's how I get comprehensive knowledge fast, and how I get all the information I need to make these videos. If you want to check out those books, articles, or podcasts you've been meaning to get through, you can grab a free trial plus 3 months free when you sign up for the annual subscription at shortform.com/staycurious. Seriously, that's 3 months totally free with my link. Alright, let's get back to it. Now, if a dust speck of your original mass somehow made it past the initial kinetic shock, and if it were traversing toward the night side, the evening terminator, you would enter the condensation zone. This transition region is characterized by a rapid temperature drop from above 2,400 degrees Celsius, to approximately 1500 degrees Celsius on the night side. This is the core engine of WASP-76b's fame, as 1500 degrees Celsius is below the condensation point of vaporized iron. The iron which was vaporized into gas on the day side is now transported by those supersonic winds across the terminator. Upon reaching the cooler night side, it drops below its condensation point, forming liquid iron droplets that are suspected to rain down. You're plummeting deeper under that 0.7 G load, into a high-pressure zone, and the precipitation hitting you isn't water. It's high-velocity molten iron. Imagine a glowing-in-the-dark cave squid of an atmosphere, but the water is metal. By 5 seconds, every part of your original structure is either stretched out across the sky at supersonic speed, incinerated into metal plasma, or assimilated into the dense layers of atmosphere, destined to fall as liquid iron in the cold, dark night side. The planet is a massive chemical separator, perpetually distilling its atmosphere of vaporized metals. WASP-76b is an astrophysical laboratory for atmospheric extremes. The primary mechanism of destruction is kinetic stress induced by those highly supersonic winds, rapidly followed by thermal dissociation and the relentless gravitational acceleration. It's a terrifyingly magnificent and utterly deadly place. The more we understand the universe's violent little star systems and the exoplanets they create, the more we realize just how rare home really is. This ultra-hot Jupiter is a perpetually flowing chemical separator, taking in atoms, mixing them up with supersonic winds, and dumping them out as molten metal rain. So, hit that like button if you learned something new about atmospheric hydrodynamics today, and subscribe for more galaxy survival scenarios. Catch you in the next one. Stay curious.